Hi, my name is Danielle and I'm a content developer here at Nvidia. I'm looking forward to being your guide during this introduction to deep learning. Studying AI can be pretty challenging, but it's also very rewarding. Not only can we learn about how robots think, but we can also pick up a few tricks to help humans be more efficient learners too. That's what this first lecture is going to be about. Excited? Me too. Let's get going. Okay, so I have my computer down here and the camera's up there, and we're going to go over some technical things before we jump into the theory. So below this video, you should hopefully see something like this that has the start button up in the top right. So go ahead and click it, and that's going to wake up our GPU. And when we do that, we can also see a copy of the slides that we're going to be going over. And what's really cool about this is down here you can expand it by pressing this open a new window. And in the bottom right here, you can also click on the notes. So this is the first slide. It doesn't have any notes, but as we go through it, we can see a transcript of what we're going to be talking about. And I also like to sneak in like little extra bits of trivia in here and some links, so hopefully that helps. All right, so when the GPU wakes up, it's going to look something like this. And when I click on this Launch Task button, it's going to take me to the Jupyter Notebook. So there's a couple more things I'd like to share with you. On the left here, we have our directory of files. Go ahead and read them in alphabetical order. When you're done, I highly recommend saving your work by right-clicking it and going to download. In the future, if you want to be able to reference that downloaded notebook, we can go ahead and upload it again by clicking this up arrow and uploading it. Now these notebooks are pretty small. Hopefully you won't run into any memory issues, but if you do, we can click here, the circle, and we can see the kernels that are running for each of these notebooks. Each notebook is a bit of a memory hog, so if we shut that down, that'll release the memory for the rest of the GPU. This would probably be a good time to go over the goals of this course. Artificial intelligence and machine learning, they're huge fields. They can take years to master. So this course is kind of like a taster, a teaser of what's to come. I like to think of it as a tutorial to an open world game. We might not be able to go through all the mechanics within the game, but it's enough to get us started and have some fun. If you're not a gamer and you're more of a gym person, I like to think of it as going to the gym for the first time in a long time. It might be challenging, and we might be a little sore tomorrow, but we'll have a better understanding of ourselves. And we'll also have a better idea of what we want to work on, whether it's our arm muscles or our leg muscles, or in this case, our math and computer science muscles. Okay, with that out of the way, I think it's time to jump into the theory, so I'm going to jump off camera. Okay, good luck. So we hope you approach this material like a fun challenge. If you take part in the coding exercises, you'll have access to the material for up to a year, so it's almost like you have infinite lives. The technical term for learning while having fun is called relaxed alertness. Our brains effectively have a gap between when we're executing versus when we're learning, much like how neural nets and machine learning models have training and prediction phases. So with all that human psychology out of the way, let's get into robot psychology. We'll start with the prologue to our story. How did we get to where we are today? Humans have been trying to teach computers to perform tasks since their invention. Early in the days in computers, many people were convinced that they would achieve human-level intelligence within a few decades. It turned out that generalized human intelligence was beyond the grasp of computers at the time. During World War II, many scientists and engineers tried to find a standard for building a computer. They played with the idea of neural networks, but they lost out to the reliability and efficiency of the von Neumann architecture. I'm not going to get into the von Neumann architecture because that's a lengthy and fascinating topic tangential to machine learning, so I'll leave some references in the notes instead. Long story short, it's the basis for modern-day computer processing units. As of recording this, chess is popular because of a show called Queen's Gambit, so I'll share a chess story about neural networks. The early 90s was an exciting time for AI because it was the first time a computer was able to defeat a reigning world champion of chess. The chess machine, Deep Blue, used mostly brute force calculation, with many hard-coded rules that specialists and programmers collaborated on to limit the board positions Deep Blue computed when looking ahead. After this momentous occasion, the AI and game world asked, "What's next?" So, they turn their eyes to backgammon. Backgammon is similar to chess in that it's a two-player turn-based game, but it differed in that many pieces can be moved in a turn, and it involved probability with rolling dice. The brute force approach with Deep Blue had difficulties dealing with games of chance, so neural networks were explored. The neural network did surprisingly well, becoming a top player and even helping to discover new strategies. But because it wasn't the best in the world, people still saw neural networks as toys. Deep Blue is an example of an expert system. These systems are meant to mimic a human subject matter expert by hard-coding many rules and took hundreds to thousands of engineers to make. Up until recently, this was the dominant strategy of automated decision-making. However, these systems had limitations. Most importantly, rules for these systems had to be understood, defined, and programmed by humans. The computer could only do as much as a human engineer was able to understand and turn directly into code. For some well-defined tasks, this was fine. But for some tasks that are simple to humans, it was extremely difficult to build rules that a computer could follow. As an example, for each of these pictures, think of one word that describes them. For the picture on the left, we can describe it as ocean, wave, or blue. For the right, we can call it taxi, or car, or headlight. And for the center, we could say it's cat, or kitty, or cute. For most adults, this probably isn't so tricky. But how will we teach a newborn child, let alone an artificial intelligence, how to do this? With children, we expose them to lots of data and help them by supplying the correct answer. A very popular learning technique is trial and error, where students make a prediction on what the correct answer is, and if they're wrong, adjust their approach. It turns out that deep learning is very much like this. So if neural networks weren't used for a long time, what changed? The first is data. In order for a neural network to learn, it must be exposed to lots of different data. For a neural network to learn what a cat is, it needs to see many pictures of cats, as well as pictures with no cats. Thanks to the internet, there's now lots of data to learn from. The other major factor is computing power. If we're effectively training an artificial brain, let's think about our own for a second. How many gigabytes of information do we observe in a given second? What's the frame rate of life? What is the resolution of the human eye? While modern AI is impressive, we humans process significantly more data in a second than an AI does. One way machines can try to catch up to us humans is with higher computing power. It turns out that under the hood, neural networks are matrix multiplication machines. What other types of problems require many matrix multiplications? Computer graphics. With computer graphics, objects are represented as many tiny triangles working together to give the illusion of something more. With animation, simulation, and gaming, these tiny triangles are often transformed and rotated, requiring matrix manipulation. Since neural networks and graphics are both built on top of the same fundamental mathematical problem, it's no surprise that the hardware for one can effectively be used for the other. An especially important invention in tackling the training of neural networks was the parallel processor. The math required to train a neural network is not especially complex, but calculations must be performed millions, billions, or even trillions of times. While a CPU might have tens of cores, a GPU can have hundreds to thousands, allowing for faster parallel processing of this task. So what is deep learning, and what makes it special? Deep learning flips traditional programming around. For example, normally to build a classifier, we come up with a set of rules and program those rules. Then, when we want to classify something, we give our program a piece of data, and the rules are used to select a category. With deep learning, we first need a list of variables, inputs, and their corresponding outputs. We don't need to know the relationship between the inputs and the outputs, but the more accurate we can observe their values, the better. We'll call this list of examples the dataset. We then train a model by showing it the dataset and the correct outputs. The model keeps taking guesses and finds out if it was right or not. It slowly learns to correctly categorize over the course of training. The fundamental difference is that instead of humans needing to identify and program the rules, a deep learning algorithm will learn them on its own. This is a fundamental shift in the way we build software systems. Deep learning is not always the right choice. If the rules are clear and straightforward, it's often better to just program it. However, if the rules are nuanced or complex, and humans would have a hard time describing them, let alone programming them, deep learning is a great choice. One thing that separates deep learning from traditional machine learning is the depth and complexity of the networks that are used. For especially complicated tasks such as natural language understanding, networks can have billions of parameters. The deep in deep learning refers to many layers in a model that learn the important rules necessary for completing a task. These are often called hidden layers. Deep learning has only been a major factor in the last decade or so, but it has had a huge impact in many industries. The field of computer vision has been around long before the field of deep learning, but because there are now more and more tagged high-quality images available, deep learning is having a large influence. The goal of computer vision is to teach machines to see and perceive images the way that humans do. Thanks to the complexity of our eyes, not to mention the processing our brains do with these images, this is no easy task. Natural language processing has helped make huge shifts, for example in highly accurate real-time language translation, as well as voice recognition and virtual assistants. Recommender systems based on deep learning fuel the internet with content-curated feeds such as Facebook, music like Spotify, video like YouTube and Netflix, as well as targeted online advertising and shopping recommendations such as Amazon. Reinforcement learning has achieved incredible results in matching human expert performance, such as the AI AlphaGo, which beat the world champion in what is considered one of the most difficult and complex games in the world. AI bots are now also taking on world experts in complex video games, such as StarCraft and Dota. Before we get too much into the theory and specifics of deep learning, we're going to act like an AI and play with the neural network right away. See if you can figure out how we went about constructing the model. Feel free to experiment and alter the code. You can always restart the GPU instance in order to get a fresh start if your curiosity gets a little too crazy. Ready to give it a try? Let's get started.